all. In this lecture, we are going to discuss Prim's algorithm. It is a greedy algorithm used to find the minimum spanning tree of a weighted undirected graph. So, for the Prim's algorithm, the input should be a weighted undirected graph. The Prim's algorithm iteratively building a tree starting from a single vertex and adding the cheapest edge. Here, the cheapest edge refers to the minimum cost edge that connects a vertex in the tree to a vertex not yet in the tree. So we keep doing this until all the vertices are included in the minimum spanning tree. Before we get into the working of Prim's algorithm, we have some key concepts here. The first one is spanning tree. A spanning tree of a graph G is a subgraph. So a spanning tree is nothing but a subgraph of a given graph, which is basically a tree, and it contains all vertices of graph G containing no circuit. So this we have to remember. If it is a spanning tree, then it should not form a circuit. Yes. Then coming to minimum spanning tree, a tree that connects all vertices of a graph with minimum possible total edge weight. So that is what we mentioned here, the cheapest edge. Okay, that is how you should form the minimum spanning tree. Coming to a greedy algorithm, we all know the greedy algorithm makes the locally optimal choice at every step with the hope of finding a global optimum. And whatever decision we are taking, all those decisions are irrevocable. And coming to a weighted graph, so this is a weighted graph. See, this is a weighted graph where graph where each edge has an associated weight or cost. For example, this edge, this is one edge. This has cost or weight as what? 10. Similarly, this is one edge. This one between 1 and 2. Between the vertices 1 and 2, we have one edge. So this has a cost of what? 25. So this is called a weighted graph. Coming to undirected graph, a graph where edges have no direction. So even if you take this example, this graph has no direction. Now let us discuss the working of Prim's algorithm. So we have three steps in Prim's algorithm. First one is initialization, second one is iteration, whereas the third one is termination. Coming to initialization, arbitrarily we can pick any vertex from the given graph as a starting point, and we can add that vertex into the MST. So this is how we should start, or we should initialize the working. Okay. Then the next part is iteration. Here we have three steps: 1, 2 and 3. Here we have 3 steps. So repeat the following steps until all vertices are included in the minimum spanning tree. What is the first step in the iteration? First, we have to identify all edges that connect a vertex in the MST to a vertex not in the MST. Okay, those edges are fringe edges. What are fringe edges? Okay, the vertex that not yet in the MST, those edges are what? Fringe edges. But it should get connected to MST. And what is the second one? Choose the edge with smallest weight among all the fringe edges. Now we have list of fringe edges. From those fringe edges, we have to identify the smallest weight fringe edge. What is the third one? Add the chosen edge and its corresponding vertex to the MST. So this is why we keep adding the vertex into the MST. Okay. And the last step is termination. Once all vertices are included, the algorithm terminates and the resulting tree is the minimum spanning tree. Now let us solve this example, this given problem, step by step. So what is the first step? We have to arbitrarily pick any vertex as starting point and add it to the MST. So here I'm picking this, I'm picking this one, this edge is into the MST. So what is the first step is, so let us have this 1, okay, 6, which is 10. So what is the next step? You have to look for the fringe edges, and from those fringe edges you have to take the min cost fringe edge. So if that is the case, from this graph, from the given graph, so we have taken 10. Okay, we have taken 10. So the adjacent of 10, this edge is this 6 to 5 and what is this? 1 to 2. So out of this, two fringe edges, 23 is the minimum. So what we have to do is, the next step is make it 23. Now we have this between 1 and 6, that is one edge, and between 5 and 6 we have one more edge, 23. So out of now we have to look for the neighbors of these vertices. So if you look up the neighbors, we have 25, this is one neighbor and this is one what to say, adjacent vertices. So out of these two fringe edges, 20 is the minimum. So what we can do is, we can go for 20. Yes, you keep adding the min cost fringes. That is the idea behind the Prim's algorithm. Okay, then now we have this 1 to 6, then 5 to 6, then 4 to 5. Now you have to look for the adjacent nodes of all these vertices. If you look adjacent nodes of all these vertices, what will happen here is, so we have 25 is 25 with one cost, and the other one is what, 22, and we have 17, we have 11. But out of all these things, 11 is the min cost, right? So what we can do is, we can include 11 with vertex 3. Now what is the next step? We have to look for adjacent vertices of this 1, 6, 5, 4 and 3. Okay, and we have to look for the min cost fringe. So if you look for the min cost fringe out of all these things, 1, 6, 5, 4, 3. So though we have 22, 25, 17, but 3 has 14 with 2. So that is the min cost fringe, right? So what we have to do is, take 2, which is 14. Okay, remember we have visited 1, 6, 5, 4, yes, 3, now 2 also. Okay, what is the idea behind the minimum spanning tree? We have to visit all the vertices exactly once, that too with min cost. Okay, now the leftover is 7. Okay, leftover is what? 7. What we have to do? We have to check for the least cost fringe out of the available fringes. So out of the available fringes, the least cost fringes were 2 to, because we have 5 to 7, which is 22. Yes, we have 4 to 7, which is 17. We have 2 to 7, which is 12, which is a min cost fringe. So that gives you the MST of the given graph. Hope it is clear. So what we did, arbitrarily you start from any vertex. Okay, this is how the algorithm says, right? Arbitrarily you please start from any vertex and add it to the MST. We started from 1 and we added that 1 to MST. Then repeat the following steps until all the vertices are included in the MST. So identify all the edges that connect to a vertex in the MST, which is nothing but the, for one, what are all the adjacent edges we have to look. Out of those adjacent edges, we need to look for the min cost edge, which is a min cost fringe. So this is how you should add your vertex to the MST. Once all the vertices are included, the algorithm terminates and the resulting tree is a MST. So this is our MST. Okay, coming to the time complexity of this minimum spanning tree. So here we are using a priority queue. Why? Every time we are extracting a min cost edge. So for that, which is nothing but a min heap. Okay. So we are using a priority queue, which is a min heap, to store and find the minimum weight edge every time. So the time complexity, we all know, is order of E log V, where E is the number of edges and V is the number of vertices. But if we are not going to use a priority queue, okay, then we need to go with every time we have to check for remaining vertices. So that time the complexity would be order of V square. If we are going to use priority queue and we are going to extract min cost edge with the help of a priority queue, which is a min heap thing, so that time it is order of E log V. if you are not using a priority queue, then it should be order of p square. So these are the few applications of Prim's algorithm. We can just have a short visit on this. It can be used in network design for finding the most cost effective way to design your network. We can have it for clustering, we can have it for transportation planning or route planning for optimizing the routes, and we can have the circuit design to make the to have the minimal wiring in the circuit. So this is the working of Prim's algorithm, which is a Grady algorithm, and this Prim's algorithm is used to find the minimum spanning tree. Thank you for watching this video.